Sass Class with Amanda. Hey. In this video, we'll cover scatter plots and correlation. Our learning objective is to use correlation to describe a linear relationship. In another video, we described direction in terms of positive and negative associations. We said that form is the functional form. In this video, however, we will specifically be using linear form. The correlation does not work or is not effective for any other form. So just remember, in this video, we're talking about linear form, even if I never say the word form again. Correlation is actually a measure of how strong the linear relationship is between x and y, okay? Between x and y. Remember, x and y are our independent and dependent variables, or explanatory and response variables. And correlation does not give much information about whether something is an outlier, so we may not talk about this at all. So the first thing we want to just say is, what is the definition of correlation? Well, correlation is a measure of strength and direction, and it's usually denoted in statistical literature as R. Because we're talking about intro to statistics, it'll be a little r. So let's just talk about some facts and properties of our correlation. The first fact or property that we want to know is that R, or our correlation, is always positive. Okay? And it's always positive when there is a positive association. Remember when we talked about positive and negative associations, we said we could think about positive and negative slope. So this means that we can also think about a positive correlation. And just using our own inference skills, R is negative when there is a negative association. We'll only mention the most important facts and properties. Alright, and one thing to know is that R can't just be less than 0, right? Because that could be negative 100, negative infinity, etc. What we do need to know is that R is always between negative 1 and 1. And this is inclusive, so it could be exactly equal to negative 1 or exactly equal to positive 1. Alright, so we have this full range of possible values, and when R is close to 0, this indicates a weak linear relationship between our two quantitative variables. Okay, so the closer R is to 0, the weaker the relationship is. Between x and y. So rather than seeing a graph with dots that might follow some sort of linear trend, dot, 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 right? So here we might have a line that goes through here. In another case, we might have a scatter plot that looks like this. Okay, and if we had to choose which one had the weaker relationship, which one is not as close to linear as possible, we would choose this one, right? Because we have many more points that have a larger distance from the line than here, right? So this must mean that the correlation of this graph is close to 0, or closer to 0 than for this graph, okay? Another thing we want to know is that correlation requires both variables to be quantitative. Correlation requires, I can't spell, requires both variables, both x and y, to be quantitative. That means correlation is not a measure of the linear relationship between two categorical variables. What does that even mean? And it's also not a measure of two variables where one is quantitative and one is categorical. Because again, what would a linear relationship mean between those two things? So just keeping in mind that the measure of a linear relationship between two variables only makes sense when both x and y are quantitative, and you'll be fine with this bullet point. Alright, and the last thing to know is that R is not a resistant measure. We didn't talk about resistance in any of our other videos up to this point, so let me just say right now, resistant means not influenced by outliers. However, we're saying that correlation is not resistant, which means it is influenced by outliers. R is influenced by outliers. And to understand this, we do need to know the formula. So R is equal to, and you do not have to have this memorized, this is for the sake of explaining what this means. So here is the formula for correlation, okay? And now you see why I do not expect you to have this memorized. Once you've reviewed the summation formula or the summation explanation sheet on our class website, you'll understand the meaning of what's going on here to the right. Here we have our degrees of freedom, and it's 1 divided by our degrees of freedom, and then within each parenthesis we see that we have our z-scores actually, except without mu and sigma, so we're using our sample data instead of our population data, okay? So this is just what the formula looks like, but the reason why I'm bringing this is so that you can see why R is not a resistant measure, and that is predominantly because we're dealing with x bar and y bar. And we know this to be the mean of the explanatory variable, and we know this to be the mean of the response variable. And what do we know about the mean? It is highly influenced and deeply affected by outliers, right? So remember when we talked about skewed distributions, right? And we said that the mean is pulled towards the tail. And what does the tail represent? It represents extreme values or outliers. Okay, so R is not a resistant measure because it's created using our mean, and the mean is not a resistant measure because it's influenced by outliers. So we just want to work on an example to test our understanding of what we just said about the correlation, okay? And you should take a minute to try and work this out on your own, and then come back to the video so that you can see if you were correct or not. Alright, so the example is saying we have a scatter plot. It's about school GPA and IQ scores, where we're looking at 6th, 7th grade students. Okay, so this is another use for the scatter plot. Before we were talking about explanatory and response variables, where we were trying to see what the relationship is between the two, indicating whether the explanatory variable actually explains the response. Okay, another use for scatter plots is just to look at two variables, two quantitative variables, and see what the relationship is between the two. Okay, and here we don't have a hypothesis of whether IQ influences GPA. We could have switched IQ and GPA and also studied the scatter plot that way. Here we just want to see what the correlation is between the two, what the form is between the two, what type of relationship we have going on here, okay? So we see that GPA and IQ do have a very strong linear relationship, because if we took a line, okay, I'm going to draw a line here, preferably a different color. So if we took a line, maybe it starts right here, right? It looks like these values are very close, okay? Very being a relative word. So we can say that it's strong, which all of these are very strong correlations, but it's not -1 or 1, because that would indicate that the points are exactly on the line, okay? This implies the points are on the line. And if you think about it, that's the strongest the relationship can be. The strongest linear relationship that GPA and IQ can have. Okay, so it makes sense that the points would lie exactly on a line. All right, so that just leaves A and B, and the way we determine whether it's positive 0.9 or negative 0.9 is by looking at whether these two variables have a positive or negative relationship. And we see that this line has a positive slope, so as IQ increases, so does GPA. So we have a positive association between the two, which tells us that our correlation is going to be the positive 0.9.
My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. We live in a world of technology. They're collecting information on your humanity. Social networks, gaming, and in-home software.
Hello, Alexa.
Statistics helps us be more aware. Haters gonna hate my spicy lyrics. Why you gotta be so mean? Pulling me towards your extreme moods, but the median never fails to center me. 50 to my left, 50 to my right. Got these correlation and regression tools, forget them fools. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. The mean of the means is the mean. The mean of the means is the mean. The mean of the means is the mean is the mean of the means is the mean is the mean. Be careful not to fall in love. Statistical seduction from above. Your shape so beautifully symmetric to the eye with a single peak so high. I hypothesize and can testify that your p-value is the smallest I've seen. Mix that with a large power and I reach ecstasy. Your residuals defy the rest. A small scale randomized pattern tells me you are the best fit. My name is Llama, and I'm here to teach you stats, skilling you up with the cold hard facts. My confidence is so high, 95%. My margin of error so nil, 110. Can you feel me? Can you feel me? I estimate your population parameter based on only one sampling. Oh, haven't the frequentists told you about me? We live in a world of data, attempting to understand life by statistical strife. The implicit bias of cops, success rate of them jocks, medical advances, and AI romances. Statistics.